About our company, we are 16 years on the market. We have just one mission. We design and produce spectrophotometers for characterization of optical coatings, mainly spectral characterization. We have technologies and know-how in the company down to the monochromator level. This means that we design hardware, software, firmware ourselves. We run mechanical design, PCB design, and optical design. These are core. Uh, this is core data which we keep in-house, and we build instruments which our customers use every day and cannot imagine working without them. Basically, most of our customers are not really customers; they are fans of our technologies. Um, this is a line of our systems. First of all, we measure flat optics, and we go from UV to long wave infrared with different systems. All of them are fully automatic. In many cases, you don't need to use any hands to measure transmission or reflection at different angles or polarizations, and all the values are absolute. We don't use any reference samples. And we are also very much active and famous in measuring of lenses as well for transmission or reflection. So basically, this is the lineup of our products and very easy to make selection. Now I will go to real cases and I will explain you the challenges and the benefits. First of all, our main system, which is called Photon RT system, the challenge was to make a broadband absolute specular reflectance measurement of, for example, gold mirror at 8 degrees and very broadband from UV to mid-wave infrared. And this system is capable to do this. Surprisingly, we do this with just one scan. So you just put the sample and the system does the whole work. To my knowledge, this is the only technology on the market which is capable to do like that. The next challenge, which our customers are facing quite often, actually in majority of the cases, is that a seamless stitching of gratings and detectors actually not seamless. They always have some steps, and they don't see a continuous spectra without these steps. I think many of you have seen images like this, and these steps are quite annoying, and you don't really know which part of the spectrum to believe. With our technologies, we pay really big attention to this. This is the example of the really measured absolute specular reflection of the laser mirror at 45 degrees angle of incidence, S, P, and average polarization. And the area highlighted in yellow, this is like this. So we don't really have that steps or artifacts which are spoiling the whole picture of the measurement. This case is quite unique and it's really outstanding. Unlike measuring optics, we had a customer which approached us saying that they are designing mid-wave infrared optical systems and they want to select the supplier of the black coating, which they use on the inner part of their optical systems. And the challenge was to select the supplier who has the lowest possible reflection. We have been testing our technology on this, and you can see this. This is an image of reflection from 8 degrees to 75 degrees from the metal part, and you can see that there is noticeable values of reflection. So our customer was testing different samples, and they were making a decision of which partner to select for their technology. UV, that's really a hot topic right now. And especially when we go to 193, 213 nanometers, as you probably know, these are the applications associated with lithography, DPV inspection, DPV metrology, beam control, all these semicon aspects. And the problem is that there is really a challenge to measure uh, laser optics or deep UV optics at different angles and different polarizations without noise, with very high repeatability, and preferably without the use of vacuum chambers or nitrogen purge. Currently, there is probably one system on the market which is a R&D based. So this system is used only for high-tech research, but not for industry. So the challenge was to make a system for industry. We have redesigned our instrument for this deep UV application, and we are very proud of having these results. This is a real measurement of the high reflection interference mirror optimized for 193 nanometer with a very, very good S&P resolution at 45 degrees angle of incidence. Another case, again, a hot topic on the market, but not really solved well right now. When we talk about the extremely cutting-edge coatings, like ultra-narrow bandpass filters, or cut-off filters with extremely steep edges, or coatings with extremely high optical density. The present technologies allow our customers to make these measurements typically on one laser wavelength. However, the real need is to see this broadband. That's one issue. And second issue, to be capable to resolve extremely narrow bandwidth of the filters or extremely low edge steepness. The video, the next video, which you will see right now, shows the real measurement which we were able to do with our latest system. This is a ultra narrow bandpass filter at 1550, and this is a real measurement with less than 1 nanometer bandwidth measured broadband. If we switch from flats to lenses, this is another challenge. As you probably know, typically when you make coatings on lenses, you have a witness piece in the chamber, which is placed in the center of the cathode of your dome or somewhere close to the lens, because there is no opportunity to measure transmission or reflection of the lenses in the vacuum chamber. However, the problem is that the coating on this witness piece really is different from the lens. There is a tooling factor. So there are many applications where the real data, real spectral data of the lens is critical. And we have had customers approaching us saying that they not just only need to measure transmission or reflection from the lens, convex, concave, spherical or cylindrical, but they want to see the profiling of the lens reflection distribution from the center to the edge. So this system, Lindsay 150, is capable to do this. And you can see the image. We actually go from the center to the edge at certain step, any step you want. And there is a robot arm inside the system which automatically changes the position of the lens against the beam. And as a result, in a fully automated mode of operation, you can get the reflectance data virtually from any lens you want. My final slide is about long wave infrared measurements. That's another challenge. It's a hot topic, obviously, because of the current changes in the overall political environment. The more and more defense applications are emerging, so the more and more needs for high quality optics optimized for mid-wave and long-wave infrared is required. So the challenge was that the customer wanted to measure transmission and reflection of flat samples. They might be quite thick. And if you take, for example, germanium, so when you are measuring transmission of such sample at high angle, you always have a beam displacement, which can be quite impressive. And what's more important, Typically, FTIR systems are used for this. They are very well designed for wavelength position accuracy. However, quite often they demonstrate confusing results for transmission measurement accuracy. So the challenge was to design a system for this application to take into account the dynamic background radiation, which is normally present while measuring in long wave infrared. And mm, we were focused on designing the dispersive type system, not FTIR. So this system is already running on the market, and the customer is very happy. And we are able to measure on a very high level uh, coatings which are optimized for long wave infrared. This is example of the polarizer at 10.6 micron, 45 degrees, or for example, AR coating, again optimized at 10.6, measured with our system for transmission and for reflection. And we believe these results are very, very superior. Uh, that's all from me for now. Thank you very much for your time. We are your reliable partner for thin film optical metrology and hope we share the same passion for optics with you. Thank you.